The main goal in selection of power is to have a nice clean transient free of signal noise. To achieve this, we want a temperature rise. In this example on stainless steel using sensor size 6.4 millimeters radius or model 33171, we've used 1000 milliwatts, which has given us a temperature rise of 0.6 or approaching 1 degree Celsius. This is of course satisfactory. We have met the minimum temperature rise, which gives us a green signal. But let's go to the extremes and just walk through what a bad or low power looks like so that we know how to identify it. So same test time, sensor size, the only thing we've changed is the power. So 50 milliwatts gives us a temperature rise of 0.3 degrees Celsius. Of course, we should increase the power to approach the minimum temperature rise and give us a transient free of signal noise. So if we go to 100 milliwatts, you can see we have increased the power and the resultant temperature rise. 150 milliwatts, the same. 200 milliwatts, and as we approach the minimum temperature rise, the color goes from a red to a different color to signal that we're approaching the satisfactory temperature rise. And as we get into the higher powers, sort of skipping ahead, you can see that once our minimum temperature rise is achieved, we have a nice clean signal. And just to give you a demonstration what that signal noise looks like is if we select two beside each other, you can see the effects of that. So we're looking to achieve, again, a minimum temperature rise so that our transients are free of noise. In this section of the TPS training, we will discuss selection of test time. Selection of test time satisfies multiple purposes, the first being the penetration depth. We want to select a time that penetrates deep enough into the material that it is truly representative. Of course, this is most critical when you have non-homogeneous materials. Reason number two, to satisfy the total to characteristic time, or TCT. This comes from thermal diffusivity multiplied by test time divided by the radius of the sensor squared. And the third reason is to stay within the boundaries of the sample, or based off the dimensions and the thermal diffusivity. A test time should be selected to achieve this. Otherwise, you can get effects of reflection. To demonstrate the concept of penetration depth, which is calculated from the measured thermal results of your experiment, stainless steel is selected and test times from 0.25 seconds to 40 seconds were measured. So by selecting each test time and looking at how far the penetration depth was penetrated in your material, and this is again from the edge of the sensor to the edge of the sample. So from the edge of the sensor in 0.25 seconds, approximately 0.3 millimeters of penetration depth. And then selection of 0.5 seconds was 3 millimeters, 1 second, 3.8, 2 seconds, 5.4, 3 seconds, 6.8, 4 seconds, 7.7, 5 seconds, 8.6, 10 seconds, 12.19, 20 seconds, 9.6. So as you can see, the longer the test time, the further the heat diffuses into the sample, resulting in a deeper penetration. Now that we have discussed the concept of penetration depth, we can discuss the important concept of total to characteristic time, or TCT. This is a unitless range of 0.3, which comes from the thermal diffusivity of your sample, measured, multiplied by the test time used, divided by the selected sensor radius squared. To vary the TCT when using the same sensor, we can just vary the test time. So if your TCT is too low, you can increase the test time, and if your TCT is too high, you can decrease the test time. It's important to point out that the 0.3 starting TCT lines up with the radius of your selected sensor. So as you change sensor sizes, that 0.3 represents the radius of that selected sensor. So in this case, looking at our stainless steel measurements we've made from 0.25 seconds up to 40 seconds, this has been done with a sensor, the sensor 33171, which has a radius of 6.4 millimeters. And as you can see from our 0.25 seconds, the TCT has not been satisfied, which in this case should be 0.3 or a penetration depth approaching 6.4 millimeters, which matches the radius of the selected sensor. So let's go to 0.5 seconds. Our penetration depth is deeper. Our TCT is higher, but we are still lower than the required 0.3 or 6.4 millimeters radius. 1 second, our TCT is higher and our penetration depth is longer. Same with 2 seconds, same with 3 seconds, and now we're approaching the minimum TCT as we approach 6.4. And the color of the TCT will change to signify that we are approaching or satisfying the minimum TCT. And as we go to 4 seconds, we have passed the minimum penetration depth and TCT. 5 seconds, now we have a higher TCT. Again, we are well within the 1.4 max range as our probing depth penetrates further than the 6.4 radius. 10 seconds, 20 seconds. You can see that as we test longer, our penetration depth is deeper and our TCT higher. In the discussion of test time and sample boundaries, we want to make sure that we select the test time that penetrates as much of the sample that's available without penetrating past the dimensional boundaries of the sample, or we will get effects of reflection, which will cause error in our data. To calculate the penetration depth available of your sample, we want to select the distance from the edge of the sensor to the edge of the sample, both perpendicular to the sensor, as well as from the radial edge of the sensor to the edge of the sample. In this example, our stainless steel pieces are 40 millimeters in diameter by 20 millimeters tall. So to calculate the minimum penetration depth for this sample, I took the diameter of the sample and minus the diameter of the sensor and divided that by 2. That gave me the distance on each side of the sensor in the radial direction if the sensor is sitting in the center of the sample. And we can compare that to the thickness and select which one is the smallest dimension. The TPS software does this automatically, but it's good to understand this concept. So the available penetration depth from the edge of the sensor to the edge of the sample is 13.6 millimeters, and the smallest dimension from perpendicular to the face of the sensor is 20. So our smallest dimension is 13.6 millimeters. So as we look at the data from these various test times on the stainless steel sample, you can see we have a large range of penetration depth available. So 0.5 seconds, we have lots of penetration depth available. So we want to select a test time that approaches that minimum, so that we're getting a representative volume of sample included in the measurement. There's 2 seconds, 5.4 millimeters, 3 seconds, 6.68, 4 seconds, 7.7, and 5 seconds, 8.6. So we have lots of range. And 10 millimeters, 12.19. So here we are approaching the radial dimension from the edge of the sensor to the edge of the sample. So as we click 20 seconds, you'll see a change in the residual pattern. Again, the residual pattern is showing the linearity of the data. What this is telling us is some of that test time at the end is actually reflecting back and disturbing the raw data. Now we can manually remove this test time from this measurement of 20 seconds, or we can select the test time before it, which is the maximum test time that allows us to use all the data points included within it. Another important aspect of test time is removing the contact resistance which exists between the sensor and the sample. This is done by removing that portion of time at the early part of the test time that represents that contact resistance. This can be accomplished in two ways. One, applying the contact correction that's available on the MP1 TPS. This automatically characterizes and removes that portion of time so that your data represents intrinsic properties of your sample free of contact resistance. This can be confirmed by investigating the residual tab. If you had any behavior at the front of the residual, that could represent, or nonlinearity, that could represent the contact resistance. The back end of the residual pattern, if you see any behavior there, that could represent effects of reflection. The second way is if you want to manually remove those points and iteratively approach removing the contact resistance. So I've added a calculation and removed the contact correction modifier and included all the data points in this calculation, so from 1 to 500. And as you can see, when we investigate the residual pattern, the heat is penetrating through a layer of kapton and air, and as the heat gets into the sample, it's diffusing in a more linear fashion. We can manually remove a few of these points and see the effects on the residual pattern. So let's remove a few points and then edit the calculation. And as you can see, that did improve the residual pattern, but there's still some more time that needs to be removed to fully accommodate that random residual pattern. So let's take a few more points. And now we have removed 10 points of 500, and you can see our random residual is much better. And this means that we've removed the contact resistance in a manual way by selecting points, recalculating, selecting points, recalculating, and looking at the residual pattern or observing the residual pattern for best fit. Now that we've discussed removing the effects of contact resistance and its effect on the residual, the second most common source of error affecting the residual is effects of reflectance. This is where the heat from the sensor approaches the boundaries of the sample and based off the dimensions reflects back and disturbs that portion of time, the test time on. We can investigate that by looking at the 10 seconds measurements that we identified was ideal for this stainless steel sample. Again, we want to select test time that are maximizing the available dimensions but not penetrating past them. So in our 10-second measurement of this stainless steel, we're probing 12.19 millimeters. And if you remember, we calculated a maximum allowable penetration depth of 13.6 millimeters. So that is why our residuals are random, as we have not hit any edge of the material and reflect it back. With that in mind, we can go to our 20-second test, which should show, and in fact does show, effects of reflection. And we can investigate this by removing portions of data from the back end of the sample. And you can do this by manually dragging the end point back so that we're removing portions of time, and I can edit the current calculation or add a new one. And as you can see, if I change this to points, we've removed roughly 70 points. So let's make that 300 so that we can see the effects of cutting 1/4 of the test time off. So I can recalculate and look at the residual pattern because of that recalculation. And you can see the residual has improved when compared to all the data. So again, this is a calculation of all the points, and this is after removing 1/4 of the 20-second test time. And I can add, let's add one more to sort of try to improve the residual pattern a little bit better. So if we switch this to points, I'm going to calculate up to 200 points. calculate. We should see that as another calculation window, and we can compare that residual. As you can see from that residual, it's now random, and we're not seeing any effects of reflection. But we've chopped off half of the available points, or 10 seconds. So with that, this data is okay, and it's fine to use data that you removed points from, especially if that's all you have and you've made measurements of longer test times. But you can also use longer test times to identify what your ideal test time is. So we've identified from this that 10 seconds is our ideal time for the available dimensions on this sample. So why not measure for the whole 10 seconds so that we can maximize the number of points used in our calculation.